Okay. Our modern view on physical chemistry is that there are no classical laws of thermodynamics. Okay. So forget about the zeroth law, the first law, the second law. Let's forget about them, right? We don't want to assume them anymore. Let's see if we can obtain them from the microscopic world. And so we instead, and again, this symbol here means there are, right, or we have, or right, you can assume that this exists, and this is a negation symbol. So we have no classical, no postulates of thermodynamics. Instead, we assume that there are elementary particles. So in particular, what you have is electrons, photons, something with a mass, right? Protons, neutrons. We can also take a little bit coarser view, and you can consider a molecule as a particle, right? It's like a quasi-particle, right? So microscopic, a bunch of atoms that stick together. The internal force is so large, we don't consider conditions under which they would separate. So effectively, it's like a particle, right? There's a physical chemist, René Fournier, at York University, who is studying, for instance, superatoms. Right? So it's a bunch of atoms, and this collection, like a cluster of atoms, has properties similar to individual atoms. Right? So this kind of ideas is actually quite useful. Right? Now, this view, right, that everything is made up of elementary particles, again, is quite new, right? So Dalton was one of the first to really establish in the chemical sciences that they're atoms, but the physicists didn't believe it, right? The physicists and they were pushing back. They proposed the idea of the ether, and there are no atoms, right? And Ludwig Boltzmann, when he was in the University of Vienna, he really, all his theories are based on this idea that we do have atoms, right? And he suffered from a lot of scientific pushback, right? And that was 1900, right? So the fact that we have atoms is not it's not been a very long time that this is established. And again, so thermodynamics predates that, right? Now, electrons are funny, right? So these are fermions. And then in the nucleus, as protons come together, you can have fermions or bosons. And so the spin of your system is an observable, right? And so when somebody challenges you, why do we need quantum mechanics, right? One of your first answers could be you needed to account for the spin. Right? So the Stern-Gerlach experiment right, was to shoot silver ions from an electric field. And so the field makes the ions deviate from the beam. And some ions were deviated more than others. And the reason for that is spin. So spin, we don't have a classical analogon to spin. But it's an observable, it's reproducible. You better wrap your head around it. It's nothing we can debate, really, right? It's not open for discussion. So any theory that doesn't account for that doesn't capture it all, right? And any theory that does account for it is of course obviously more powerful, as long as it also accounts for all the rest. So now this is sort of course with other experiments like the excitation series, right, for light emission of the atoms, or the black body radiation. You probably heard about all these cases in your quantum mechanics course, right? All of this is why we have quantum mechanics. Now, in quantum mechanics, in the most common form, we use the wave mechanics. So we have a Hamiltonian operator on the wave function, and that gives you an eigenvalue and the wave function. So there's a differential equation, right? And I believe you also have encountered differential equation already in your math courses, right? So just think of it, it's just a differential equation, right? And the solution to this differential equation gives you the eigenvalue and this function, a wave function, right? Now, you know that these solutions, there can be multiple solutions, right? So we should denote the solution with an index, right? So it's more than one solution. And that's your eigenvalue spectrum, right? So this equation is, of course, key for this course, right? This equation, we want to connect this equation to the macroscopic observables. So we have to know a little bit where this equation comes from. And as far as I know, you're not familiar with this. This is the Hamiltonian. Okay. So where does the Hamiltonian come from in physics? Anybody?
The representation of energy eigenstates.
The energy eigenstates, the states are the wave function solutions, these I's, right? This could be your molecular orbital or a certain mode, a vibrational mode, right? This would be your state. And the energy would be the eigenvalue here, right? But what this operator, right? You discussed this operator in the quantum mechanics course, but where does it come from? Right? So this is actually was a major breakthrough that actually came out of classical mechanics. Okay. And classical mechanics really started with Newton. And so I want to just very briefly comment on this, because what you probably also learned is that the Hamiltonian in the postulates of quantum mechanics, it's constructed due to the correspondence principle. So people consider the classical terms and they use them in the Hamiltonian, right? So it's a classical mechanics derived concept, right? And so we have to know where this comes from, and it's not it's not very advanced knowledge. It's if you study physics, the classical mechanics leading up to the Hamiltonian happens in the first or second year of your undergraduate studies. Right? We are not going to do that, of course, but you should know about it, right? So in Newton, we have this postulate, right, that the acceleration times the mass, right? This is the second order time derivative of the position. And that's Newton's postulate. This thing is the force. Now, we talked on Tuesday about the importance of energy. The force is the derivative of the energy, right? So that Newton's first law says that if you don't act with some force on an object, it will not change. That's akin to conservation of energy. Nothing will change, right? Unless you put in, you provide some force or some energy. There was a question?
Oh, I'm sorry, what's the dot explanation?
Yeah, that's we postulate that equation, right? You impose it. So Newton simply postulated this. There's no proof for this. This here represents the audacity, if you wish, of somebody just trying something. And then it turns out to be right, of course, right? And then you can show things afterwards. But it's not at all obvious, right? There were precursors. Aristotle postulated that actually the force is rather proportional to the velocity of something, which is not a bad idea if you have friction. So if you have a lot of friction, right, the faster you want to push something, the more force you have to exert. Right? So that's where it comes from. But Newton actually then argued and realized, no, you need to go one differential order higher. It's the acceleration. Right? So what does this mean, right? This means we have a second order differential equation. Right? If you want to write down your equation of motion. The equation of motion gives you x as a function of t, right? So over time, right, you can think about Taylor expanding your axis in time, and so you predict the future, right? If you know the acceleration now. And you know the acceleration now if you know the force you're spending. And you know the force you're spending because you're burning some energy. You're consuming energy. You can stick a thermometer to it, or you can count the atoms you've been burning. You know how much energy you're providing. That tells you how much it's accelerating. You can also measure the particle or the object moving over time, right? And then the velocity and its acceleration will tell you how much energy you consume. So you can check this, right? And then you predict the future, and then you see if your prediction was right? And then you have validated experimentally Newton's second law. It's quite straightforward. Now we have Avogadro's number of particles, right? So we have 10 to the 23 positions in X and Y and Z. So this means we have 3n differential equations. And second order. If you remember from your differential equation class, second order is no longer easily solvable. First order we can usually do, but not second order stuff. And so that's a problem. People didn't like it. And also, this typically happens in X and Y and Z, right? And so it's difficult to actually imagine you have some boundary conditions, right? And so there was a more abstract development, which was done by Euler and Lagrange, who recast this problem, right? And let me add up here, this force, of course, is dxe. So here you have the energy I praised so much on Tuesday, right? So Euler and Lagrange made this more general. They said, oh, let's forget about x, y, z. Let's generalize the coordinate, any coordinate, right? It doesn't have to be rectilinear. Could be curved, right? We can have some constraints when something is moving on a trajectory, right? And for every constraint, this maybe you also recall from differential equations, you should be able to eliminate one equation or one variable or something like this. So you really, constraints are your friends, right? The more constraints you know, the fewer equations you have to solve. So Euler-Lagrange, and this is the Lagrange from the Eiffel Tower. If you go there, it was a student of Euler. They varied this in this sense. So Q is the generalized coordinate, right? As opposed to a Cartesian coordinate. And so you see, this looks a little bit like the derivative of the energy with respect to x, right? So instead of x, you have a q. And instead of the energy, you have what's known as the Lagrangian. So this is a kind of force. The Lagrangian is actually the difference between the kinetic energy and the potential energy. So this, it's again a kind of energy. And so what they showed is that this is the time derivative of the derivative of the Lagrangian with respect to the time derivative of q, which is a momentum, right? The first order time derivative of a coordinate is a momentum. So now you have something analogous to Newton, right? And you do this for every coordinate. So there are many of such equations, so the Euler-Lagrange equations. And the main advantage is that you have this in generalized coordinates. 1 second. What's the point of generalized coordinates? The example I like most is the pendulum, right? So imagine you have to describe the movement of a pendulum over time, right? Now imagine doing this with Newton. Then you have an x coordinate and a y coordinate. You have to solve Newton's equation. Second order differential equation, x and y. Euler-Lagrange instead tells you I can also, because I know that this length here, the pendulum, I can presume it's fixed. It's rigid, it never change. So instead, I could also use simply this angle here as the coordinate. Then I only have one differential equation to solve. Half the work. you ever solved the second order differential equation by hand, you will appreciate that. It can literally take hours. So, now it's still a second order differential equation, and that's really hard, especially if you don't have computers because you were born in 18th century or something. Yes, excuse me.
In that, what's the difference between that and just total energy? The difference between kinetic and potential. Isn't that just total energy, or is that specifically different in this scenario?
No, the total energy is the sum of the two. And that's what we are coming to. It's a different energy measure. It's also an energy, right? Whenever somebody comes to you and says, oh, but the energy is going up or down, you should always be asking which energy. And there's many different energies. And now, what drives things for us, as mentioned on Tuesday, are the free energies, right? Usually under usual conditions. Under very controlled lab conditions, it's just the total internal energy. And that is closely related. So these energies are closely related to each other also. So they're transforms that can get you from one to the other, right? So mathematically, they're closely related. But if you want to predict your experiment, you have to be careful that you're using the right one. Now, very good, your comment, because really annoying second order differential equations. And now in comes Hamilton, the Hamiltonian mechanics. So this historical pattern, right? Newton was, I don't know, 17th century, Euler-Lagrange somewhat later, and then Hamilton sometime 19th century. Don't quote me on these numbers. I'm not, I like history, but I don't memorize these. Anyhow, so Hamilton comes in and shows that actually we can use these equations, the derivative of the Hamiltonian with respect to a momentum p is the time derivative of the generalized coordinate, and the derivative of the Hamiltonian with respect to q is the negative of the time derivative of the momentum. Okay. So this right-hand part is very similar to, again, Newton, right? So Hamiltonian is some energy form again. In fact, as just said, it's T plus V, okay? And so what you have now is, if you look at these two equations, these are Hamilton's equation of motion. Right? These two equations are what the Euler-Lagrange equations are in Lagrangian mechanics, and they correspond to what Newton's equation is in Newtonian mechanics. Now, this is much preferred. Any guess why? The reason is that you have twice as many as equations, right? There's 6n equations. But they are all first order differential equations. So Euler-Lagrange eliminated redundant differential equations second order easily. But Hamilton changed the order from second to first. And that's really an order of magnitude improvement in ease of solving them, right? So everybody is super excited. Classical mechanics, 19th century, Hamilton mechanics, right? That's all of physics is done like that. And that is the reason why there is no Newtonian mechanics in your quantum mechanics. Right? That's why we have the Hamiltonian, right? And so that's why we want to describe things in terms of momentum. So your Hamiltonian here, as you would typically encounter it, the momentum squared over 2m is the kinetic energy. And then you have some potential, which depends only on the coordinates, independent of momentum. Right? So this is a super simple mathematically much simpler structure. And so that's what we want to make use of when we go to quantum mechanics. So we basically reduce these the degrees of freedom, right? We increase the degrees of freedom. We have 6 instead of only 3, but we have simpler equations of motions. Right? Okay. Are there any questions so far? Pretty good. Did you know about this? Who knew about this? Right? That's typically what we get in quantum mechanics. Right? For chemists, we just tell them this is your Hamiltonian, and they say, "Well, what's a Hamiltonian? Where does this come from?" Right? Okay, so you can trust me. It's even on my YouTube channel. I taught classical mechanics once, but it's in German, so maybe you don't want to follow that unless you're German speaking. But the derivations of all of these steps, they build on top of each other, right? So it's extremely rigorous. It's you can there's no chance in hell that there's a problem with this, and it builds on it. So if you use Hamiltonian mechanics, that's as good as using Newtonian mechanics. It's just the way how you compute things that's smarter, right? Now, in the microscopic state, and that's particularly relevant for us in statistical mechanics, we consider these atoms as points, right? And so if you have some momentum and some positions, and now I'm writing them as vectors because there are many, for every element I have a position, and for every element I have a momentum, right? So now I can consider, and this is what we call the phase space, and is spanned by all momenta and positions. Now, it's not wrong to think of them in terms of a Cartesian space, right? But it's more general than that. So you can easily, with a coordinate transform, go into another reference frame, right? So, and then we look at a bunch of atoms. And these atoms will move over time, right? So this is atom 1, atom 2, atom 3. And now over time, they will go somewhere, right? It's still the same atoms, right? So these are n atoms at T. And these are the same n atoms at T plus delta T, right? That's how momentum and position have changed over time, right? Now, I can consider all these n atoms as one system, right? It's your entire system. And your entire system then lives in these 3n coordinates and the 3n momentum. And it's just one point. And it's moving somewhere else at T plus delta T and at T. And this is the trajectory. Right? So your atoms are moving perpetually. Right? Even at 0 Kelvin, right? we have a quantum movement, the 0-point vibration and energy. So they'll be moving, and the question is, how do they move over time, right? And so that's why we have to look at the dynamics, right? And that's how time enters the picture. That's why everybody's talking about classical mechanics. That's what Newton started doing, right? Let's look at how things move with time. So the time evolution is given by following. Other words people use are also solving or integrating the equations of motion, EOMs, of Hamilton. You take your pick, Lagrange or Newton. So in this phase space, and I'm really just glancing very crudely on this, right? So I'm not giving justice to the whole depth and complexity of all the assumptions that went in there. But just for example, these lines here, they can never cross. if two particles have the same position and the same momentum, they would be identical. And so the time derivative would become ill-defined. In this phase space, right? So it's first order. Right? We don't have acceleration. It's just momentum and q. So anything that's in the same point in phase space is the same. So any two particles, that would be fusion, right? Nuclear fusion or something. You can't have that. So that tells you something, right? These trajectories, particles can move, right, freely, but not anyway, right? It's not total freedom. It's not anarchy. So this is sort of where Schrödinger enters, and then what do you have in quantum mechanics, right? So we are talking the likes of Planck. So Planck was 1901. Schrödinger was 1925, right? So 100 years ago. Well, of course, you have the time-dependent Schrödinger equation, right? Why do we have a time-dependent Schrödinger equation? Here you have your time derivative. That's the psi dot. Instead of a q dot or a p dot, you have a psi dot. Right. So once you went through the exercise in classical mechanics, it's obvious your psi has to have a dot. Right. For us as chemists, it's like crazy. Where does this come from, right? I hope that this is a little bit clear now. So and then we usually say, oh, okay, the time dependency is really complicated. So let's just focus on this part here. Okay. To begin with, right? So I don't know if in the quantum mechanics course you talked about time-dependent solutions to Schrödinger equation. You did? Some? Okay. Right? And that's really cool, but usually it's much more complicated than the time-independent, right? And so for this course, you will not need the time-dependent one. Right? We'll be doing statistical mechanics, right? And so the quantum dynamics of quantum particles is something that's like a grad course level, right? So statistical mechanics, the introductory course like this one, is without quantum dynamics. It's just classical dynamics, but classical dynamics using quantum energies. So this might sound really confusing. But you'll see, I think. Okay, so let's have an example. Your favorite, maybe Schrödinger equation. The particle in the box. Your Hamiltonian is basically the kinetic Hamiltonian. Right? You have some boundary conditions, but so you and some mass. But what you see here is the second order derivatives that enter here. Right. Now h bar is h over 2 pi, the reduced Planck constant. You probably encountered already. Now, when you solve this, you arrived at eigenvalues for some particle K, right? And this is the 3D box, right? Yeah. So this is a particle, right? Literally in the cube. You don't care how this cube was made, right? It's just impossible for this particle. The potential is infinitely high. So the particle will not penetrate far into this cube, right? Or not at all, depending how exactly you define it. But anyhow, so the solutions to this is that you have a quantum number in every dimension and then you have to multiply with 8 the box length. And this is a cube, right? All lengths are the same over the mass. And then you have the quantum numbers squared. All right. So for your Schrödinger equation, this means you have a spectrum of solutions here, right? So Nx, Ny, Nz. Each solution has a different wave function, right? A different state. Some can be degenerate, but solving this, right, gives you these eigenvalues as solutions, right? So you there are two parts, right? You want the eigenvalues and you want the wave functions, right? Once you have the wave functions, you solved the problem fully, right? If somebody gives you the wave function solution, then you can just let the Hamiltonian operate on it, and it dumps out your eigenvalue, right? But there are sometimes ways, and maybe you also encountered it already, to arrive at the eigenvalue solutions without having to solve the wave function. So that can also happen. So then you would know just the eigenvalues. So if you plot the energy, then we see that the eigenvalues grow quadratically, right, as you increase n. For the harmonic oscillator, the eigenvalue spectrum is equidistant. So this is for the particle in the box potential. Sorry, this is a bit confusing. Let's put V as a function of X. This is not a V, this is the potential, right? And then for the Coulomb potential, like you would have it in a nucleus, right? The protons pulling in your electrons with 1 over the distance, right? Your spectrum is increasingly denser, right? It actually shrinks with x to the -2. So this gives you a spectrum of solutions. And now for one microscopic system. How on earth can we go to Na 10 to the 23? Okay. Start Mac is the answer. Are there any questions? It's not the case. I'd like to thank you for your attention. I'll see you on Tuesday.